Hello everyone. So here's the second problem from my final exam. And the first question was, write down the Taylor polynomial of degree 4 around x equals 0. So what is that? Well, since a Taylor polynomial around a point A only has to be defined in a punctured neighborhood, meaning it only has to be defined around that number, not really precisely at that, it's perfectly fine to just write down the Taylor polynomial of this around 0. So even though it's not defined, we know that we can just use the limit and such. So okay, the Taylor polynomial for that, actually we can just use, okay, firstly just the Taylor polynomial for sine, which is x minus sine 3 x, what the fuck am I saying? X minus x3 over 3 factorial plus x5 over 5 factorial, and then plus our big O of x7, and then just divide this by x. And this is equal to 1 minus x squared over 3 factorial plus x4 over 5 factorial plus big O of x to the power of 6. Yes, and now we're done with that. Wait, I need some chalk. Here you go. Okay. And now, so yeah, we're done with the first one. Easy points. And now we need to justify, and also we can note that, okay, well, yeah, nice. It turns out that the function value of this Taylor polynomial at 0 is 1, which is exactly what we wanted. And of course, also it makes sense because the limit of sine x over x as x tends to 0 is 1. So yeah, it works. And in B, we were supposed to justify. I've looked at the correct answers, and well, yeah, I just don't like the word justify in this sense. Exactly, we were supposed to justify why this is the Taylor polynomial of sine x over x at x equals 0. And to do that, we basically just need to state the uniqueness of the Taylor polynomial for sine. So actually, in the way my professor did it, he did it super simplistically. You could also do a quick little proof by contradiction, kind of. So one could say that, okay, suppose there exists a Taylor polynomial of called P, which also works as a Taylor polynomial for sine over x, but it's not equal to what we've written down here. Then, of course, since the Taylor polynomial for sine is unique of any degree, then we would know that x times p of x should just be equal to sine x. And we know that x times our polynomial that we wrote down there would also be equal to sine x. So therefore, these two would have to be equal. Which would contradict the first statement that they were not equal, so therefore we'd reach a contradiction and would be proven. So, but yeah, you didn't need to write that apparently. So yeah, that was an acceptable justification, at least for him. And 3. Use the Taylor polynomial to approximate the integral from 0 to pi half of sine x over sine. Yes, exactly. And to do this, okay, we just plug everything in, so we get the integral of this from 0 to pi over 2. So therefore we would get x minus x3 over 3 times 3 factorial plus x5 over 5 times 5 factorial from 0 to pi over 2. And then you just, okay, of course it's 0 when you plug in 0. So then we would just plug in pi over 2 everywhere, so that we get, okay, we get pi over 2 and then minus pi 3 over 2 to the power of 3 times 3 times 3 factorial. Here we can just write this down as 2 to the power of 4 times 3 to the power of 2. And plus, here again, okay, we just have pi to the power of 5, and then 2 to the power of 5 times 5 times 5 factorial. So that is the answer to C. That was not as complicated. And now for D, estimate the error in the above approximation. So yeah, give me 1 second. Okay, I'm back. So now we need to use an explicit error term, not just the big O here. So how do we do this? Well, we use the Lagrange error term, which would then be, okay, so we have that, okay, firstly we will denote the error term here. So we basically do this another time. So we have the error term for sine of x to the power of 7, and then we just divide by 7. So what would the error term for sine at degree 7 be? Or the error term for the Taylor polynomial of degree 5 of sine of x. What would that be? Well, okay, so we have sine, the 7th derivative of sine, and then, okay, so yeah, what would that be? Well, okay, if you take the derivative 4 times of sine, that doesn't change anything, and then we take it 3 times, meaning we just take the integral, so therefore we have negative cosine. It becomes cos and then minus sine and then minus cos. Okay, so we have minus cosine of some value here, and then we would have, okay, and then times x to the power of 7 divided by 7 factorial. Because we're dividing by x, we have x to the power of 6 over 7 factorial. And this is our error term, let's call it, of x. So what would then okay, so we can just first note that we only care about the absolute value of the error term, right? So we could just jump to the computations actually. So we would have the integral from, since we're integrating this whole thing and then plus the integral, and when you have plus a function inside of an integral, you can split them up. So basically all we have to do is just find out the integral from 0 to pi half of the absolute value of the error term. So what is this? Okay, well, yeah, we can write down. Okay, so we have 0 to pi half, and then we have times, sorry, dx. I always forget. So we have times cosine of some value, and then times x to the power of 6 divided by 7 factorial dx. Now, what the fuck is this? So, okay. or not what is this. Of course, we don't know what this value in here is, but we can state that this thing, because we have cosine of something between 0 and pi half, so that's the entire positive range of cosine. So therefore we can just state that this is strictly less than or equal to, we should say, the integral from 0 to pi over 2 times x to the power of 6 over 7 factorial dx. And what is this? Well, if we integrate that, then we would of course get x to the power of 7 over 7 times 7 factorial from 0 to pi half, and then we just plug in pi half to the power of 7, and then we would get our answer. But I'm not going to write that out because I don't have any more space. So yeah, that was all for question number 2. So thank you so much for watching, and now let's move on to question number 3.